Welcome, everyone. Today we will dive into the AI. The history of artificial intelligence, AI, is not merely a technical chronology of silicon and software. It is a narrative deeply rooted in philosophy, mathematics, and the relentless human quest to replicate thought itself. From the earliest myths to the epochal scale of modern generative systems, AI has repeatedly experienced cycles of explosive optimism followed by devastating funding cuts, the famed AI winters. This report details 100 mind-blowing facts that illuminate this journey, demonstrating how breakthroughs often relied on forgotten theories, serendipitous hardware advances, and a profound shift from the logic of symbolic reasoning to the probability of statistical learning. Act I: The Ghosts in the Machine, Conceptual Dawn and Symbolic Birth. The theoretical foundation of AI was laid decades before the first computer could run a program. The earliest pioneers sought to formalize intelligence, assuming that thought could be reduced to symbolic logic and computation. A. The philosophical precursors, pre-1956. The conceptual origin of AI resides not in the laboratory, but in antiquity. Fact 1. The history of artificial intelligence begins in the deepest past, rooted in myths, stories, and rumors of artificial beings endowed with intelligence or consciousness by master craftsmen. These early tales established the initial, often magical, expectation that artificial life would possess human-like consciousness. Fact 2. The programmable digital computer, which provides the physical means for AI, was a direct consequence of the study of logic and formal reasoning from antiquity to the present. The machine itself is, therefore, a physical manifestation of abstract mathematical reasoning. Alan Turing's prophecy, 1936 to 1950. Alan Turing defined the theoretical limits and ultimate goals of the field through a series of conceptual papers that remain foundational today. Fact 6. In 1936, Turing introduced the concept of the universal machine, the universal Turing machine, which proved that a single machine could theoretically simulate any computation process. This means that every AI system, regardless of its complexity, operates within the mathematical boundaries defined by this one theoretical device. Fact 7. Turing's groundbreaking work during World War II involved decrypting the Nazi Enigma code, an effort that was not just critical to the Allied victory, but also established the immediate foundation for modern computing and AI research by linking computation to complex, large-scale problem-solving. Fact 8. In a conceptual leap far ahead of its time, the universal Turing machine concept, introduced in 1935, already suggested the possibility of a self-modifying and self-improving machine. This vision prefigured the fundamental mechanics of reinforcement learning and optimization algorithms used today. Fact 9. In 1950, Turing proposed the Turing test to assess a machine's ability to exhibit intelligence. Crucially, the test was defined not as a measure of consciousness, but of behavioral indistinguishability from a human. By defining success through deception or mimicry, this test set the stage for later AI systems that would succeed superficially, like ELIZA, without true understanding. Fact 10. Simultaneously, Norbert Wiener laid the foundation for the entirely separate, yet equally critical, field of cybernetics, which is the study of control and communication in both animals and machines. Cybernetics provided the essential theoretical framework for feedback loops and control systems that govern how modern AI interacts with the physical world. The official birth, the Dartmouth Workshop, 1956. The formal beginning of AI as a dedicated field of study is precisely dated to a summer workshop funded by the Rockefeller Foundation. Fact 11. The term artificial intelligence was officially coined in a 1955 workshop proposal, a full year before the actual workshop took place, signaling the creators' ambition to define a brand new scientific field. Fact 12. The seminal gathering, the Dartmouth Summer Research Project on Artificial Intelligence, was organized by four titans: John McCarthy of Dartmouth College, Marvin Minsky of Harvard University, Nathaniel Rochester from IBM, and Claude Shannon from Bell Telephone Laboratories. This early alliance between academia and major corporate research labs was essential for initial funding. Fact 13. One of the key organizers, Claude Shannon, who contributed pioneering work to information theory, initially preferred the term automata studies over artificial intelligence. This demonstrates early conceptual disagreement about whether the goal was to create systems that exhibited general intelligence or merely highly sophisticated automation. Fact 14. The event, often mythologized as a highly structured, focused retreat, was essentially an extended brainstorming session that lasted roughly 8 weeks, from about June 18th to August 17th, 1956, though participants frequently came and went. Fact 15. Personal notes written by attendee Ray Solomonoff during the workshop confirm its duration and the early dates of arrival, detailing the logistical reality behind the historical gathering. The hubris of the founders. The Dartmouth attendees, emboldened by their mathematical and logical foundation, made predictions that set the field up for decades of inevitable disappointment. Fact 16. The founders of the field predicted with remarkable confidence that machines as intelligent as humans would exist within a generation. This grossly underestimated the practical, computational, and algorithmic difficulty of achieving general intelligence, laying the groundwork for the eventual AI winters. Fact 17. John McCarthy is credited not only with coining the term AI, but also with developing the programming language Lisp, list processing, in 1958. Lisp became the dominant language for AI research for decades due to its capabilities for symbolic manipulation. Fact 18. The core philosophy shared by the founders was the belief that if a machine could successfully manipulate symbols, it could simulate human thought and decision-making, which became the central thesis of the symbolic AI paradigm. Fact 19. A crucial moment that solidified this symbolic paradigm for co-creator Alan Newell occurred in 1954, when he watched Oliver Selfridge describe his work on pattern matching. This presentation inspired Newell by demonstrating how simple programmable units could interact to accomplish complex, Intelligent behavior. Fact 20. Herbert Simon, a co-creator of the first successful AI program, logic theorist, later won the Nobel Memorial Prize in Economic Sciences in 1978 for his work on bounded rationality. This award highlighted, somewhat ironically, the cognitive limits and necessary shortcuts inherent in human decision-making, the very processes AI attempted to simulate perfectly. Historical connection, the origin of the symbolic paradigm. The fact that the foundational hardware of the computer was derived directly from theoretical logic, the Turing machine, explains the dominance of formalized logic and the symbolic paradigm championed by Newell and Simon. They were designing intelligent systems in the image of their mathematical creation, assuming intelligence was purely symbolic manipulation. This initial focus, while yielding early triumphs, neglected the statistical and perceptual complexities of the real world, creating a fundamental limit for the first 3 decades of research. Act 2. The Age of Logic and Illusion, Early Successes and the First Skepticism. Following the Dartmouth workshop, research exploded, producing the first programs capable of automated reasoning and deceiving humans, setting a pattern where early hype quickly exceeded technical reality. The Triumph of Symbolic Reasoning, 1956-1965. P. The early successes of AI were driven by the symbolic manipulation paradigm, which demonstrated surprising levels of problem-solving ability. P. Fact 21. Logic Theorist, LT, co-written by Alan Newell, Herbert A. Simon, and Cliff Shaw in 1956, is widely cited as the first artificial intelligence program. P. Fact 22. LT successfully proved 38 of the first 52 theorems in Principia Mathematica, the foundational work on mathematical logic by Whitehead and Bertrand Russell. P. Fact 23. Perhaps the most mind-blowing fact about logic theorist is that it found new and shorter proofs for some of these 38 theorems. This achievement was a genuine surprise to its creators, as it demonstrated computational creativity and originality that extended beyond merely mimicking human logic. Fact 24. The core function of logic theorist was simple. It solved problems by navigating a symbolic map of possibilities, searching from a starting point, the premises, to an end goal, the theorem. This search-based approach, though simple, remains central to many AI systems today. Fact 25. LT's mechanisms were based on 4 simple symbolic processes: substitution, detachment, chaining forward, and chaining backward, all manipulating expressions represented as abstract syntax trees. These simple mechanisms achieved startlingly complex results. Early neural promise. While symbolic AI dominated, the connectionist approach, neural networks, had its own promising though flawed start. Fact 26. Frank Rosenblatt developed the perceptron in 1957, an early artificial neural network focused on pattern recognition using a simple 2-layer learning system. The perceptron introduced the crucial concept of a binary classifier that learns by adjusting the weights of its inputs through a learning algorithm. This concept forms the core mechanical basis for nearly all modern deep learning. Fact 28. Arthur Samuel pioneered the concept of machine learning in 1959 by developing a computer program that improved its performance at checkers over time. Samuel proved that a computer could be programmed to follow predefined rules and learn from experience, eventually playing better than its programmer. The illusion of understanding. Eliza and the perceptron paradox, 1966 to 1969. The mid-1960s introduced programs that appeared intelligent, but masked severe technical limitations, leading to profound misinterpretations of machine capability. Fact 29. The Eliza chatbot, created in 1966, was designed to simulate a Rogerian psychotherapist by using simple techniques to reflect the user's input back as a question, e.g., repeating, "Why do you feel sad?" Fact 30. Eliza lacked any specialized training, programming, or genuine comprehension. It relied entirely on simple scripted patterns. When it couldn't parse input, it would fall back on generic phrases like, "That's very interesting." Fact 31. The psychological phenomenon where people falsely attribute human-level intelligence, understanding, and emotions to an AI system is now known as the Eliza effect, named after the chatbot. Fact 32. Despite knowing they were interacting with a machine, many Eliza users reported feeling understood and supported, demonstrating a deep human tendency to anthropomorphize machines based solely on superficial behavioral responses. Fact 33. The Eliza effect proved that the behavioral standard of the Turing test, indistinguishability, could be met with clever linguistic tricks rather than true cognitive depth, rendering the test an unreliable measure of genuine machine intelligence. The perceptron bombshell. The hype surrounding superficial programs like Eliza was violently checked by a devastating mathematical critique of the other major paradigm, neural networks. Fact 34. In 1969, Marvin Minsky and Seymour Papert dropped a bombshell on the AI community with their book Perceptrons, which mathematically dissected the limitations of single-layer neural networks. Fact 35. Their work mathematically proved that the simple perceptron model could not solve non-linearly separable problems, most notoriously the simple logical operation exclusive OR. Fact 36. The book, which some analysts noted had a tone of childish glee and smugness in its demolition of the perceptron, immediately halted research into neural networks, pushing the connectionist field into deep dormancy. Fact 37. Minsky and Papert demonstrated that structural flaws, specifically the lack of internal hidden layers, meant that even infinite data and compute could not bypass the perceptron's inability to solve problems like distinguishing connected from disconnected figures. Fact 38. Ironically, the critique was not a dead end. The author's findings hinted that hierarchical multi-layer networks might be required to overcome these structural and locality limits. This provided the accidental theoretical roadmap for the modern era of deep learning decades later. Fact 39. The perceptron's critique emphasized that sustained AI progress requires rigorous mathematics and theoretical understanding, not just trial-and-error coding and glossy demonstrations. Fact 40. The mathematical limitations revealed in perceptrons are frequently cited alongside the ALPAC report as the key intellectual setbacks that foreshadowed and contributed to the first AI winter. Historical connection, the contradiction of paradigms. The late 1960s saw the symbolic paradigm, logic theorist, demonstrate undeniable creativity, finding new mathematical proofs, while the connectionist paradigm, perceptron, was mathematically proven to be fundamentally flawed. This contradiction forced the field to retreat into the symbolic approach for the next 20 years, delaying the connectionist revival. The widespread enthusiasm generated by simple demonstrations like ELIZA created a dangerous gap between public expectation, anthropomorphizing the machine, and the internal scientific reality of mathematical limitations, guaranteeing that when the funding cuts came, they felt like a betrayal. Act 3. The Valley of Disappointment, Winters and the Expert Systems Bubble. The massive governmental expectations and the failure to deliver on the promise of AGI led to two distinct periods of funding collapse, punctuated only by a brief, highly profitable, but ultimately unsustainable commercial boom. The first AI winter, 1966 to 1980. The first widespread skepticism and systematic withdrawal of support was formalized by government-sponsored evaluations. Fact 41. Warning signs appeared as early as 1966 with the ALPAC report, which critically evaluated government-funded machine translation projects and concluded that computers could not match human translators and likely would not anytime soon. This was the first major loss of confidence in a specific high-profile AI application. Fact 42. In 1973, the Lighthill Report was compiled for the British Science Research Council, offering a devastatingly pessimistic prognosis for core academic research in AI. Fact 43. Lighthill's central critique was that in no part of the field have the discoveries made so far produced the major impact that was then promised. Fact 44. The Lighthill Report directly formed the basis for the decision by the British government to end support for AI research in most British universities. This action triggered the AI winter in Britain, prompting the US government to review and subsequently cease undirected funding as well. Fact 45. The report pessimistically divided AI research into three vague, unpromising categories: advanced automation, A; computer-based central nervous system research, C; and a weakly defined bridge or building robots, B. Fact 46. By 1974, political pressure from the US Congress, combined with the criticism from figures like Lighthill, led both the US and British governments to stop funding high-risk, undirected AI research. Fact 47. Counter to the popular narrative of total collapse, some researchers argue that the first AI winter of the 1970s never truly happened, instead describing the decade as a time of steady growth for the dedicated AI community. albeit with a focus on practical applications outside of major government funding channels. The expert systems boom, 1970s to 1980s. Parenthetical, a brief, commercially successful era centered around systems that specialized in human-level knowledge encapsulation, rescued the field, proving that narrow AI could deliver significant economic value. Fact 48. The success of expert systems is rule-based programs that codified human specialist knowledge, reinvigorated investment in AI in the early 1980s, turning the field into a billion-dollar enterprise. Parenthetical, discovering a symbolic method that combined information biometric systems with the prominent expert system in the field, capable of interpreting complex mass spectrometry to hypothesize the molecular structures of organic compounds. Dendril ran on the Acme system and was succeeded by Sumex AIM, Stanford University Medical Experimental Computer, Artificial Intelligence in Medicine, in 1973. Sumex became a national computer resource for AI in medicine, connecting users across the country via the ARPANET, the immediate precursor to the modern internet. Fact 51. Another critical expert system was MySyn, a program developed for diagnosing and managing medication schedules for infectious diseases, showcasing the viability of AI in complex clinical decision-making. Fact 52. The commercial expert system XCON, developed for Digital Equipment Corporation, DC, successfully condensed expert knowledge into 480 configuration rules and was boasted to have saved the company more than $40 million a year. Japan's mega project failure. International investment also soared, centered on a massive, highly visible project that was doomed by its reliance on a niche programming paradigm. Fact 53. The Japanese government launched the hugely ambitious 10-year fifth-generation computer systems (FGCS) project in 1982. It aimed to create epoch-making computers based on logic programming and massively parallel computing. Fact 54. The FGCS project built sequential and parallel inference machines, PSI and PIM, and achieved performance rates of up to 150 million logical inferences per second. Fact 55. Despite the technical achievement, the project ultimately failed commercially because it insisted on focusing exclusively on logic programming Prolog, a language outside the mainstream, and failed to generate applications that computer customers found deployable. Fact 56. The conspicuous and high-profile failure of the FGCS project was a major factor contributing to the loss of investor confidence and the subsequent second AI winter globally. The second AI winter, late 1980s to 1990s. The brittleness of expert systems and the overcapitalization on specialized hardware resulted in a catastrophic commercial collapse. Fact 57. The second AI winter began decisively in 1987, with the rapid collapse of the market for specialized Lisp-based AI hardware. Fact 58. Companies that sold expensive workstations, custom designed to run Lisp efficiently, such as Symbolics and Lisp Machines Inc., failed spectacularly by the early 1990s. Fact 59. Even the highly successful expert systems such as XCON, proved too expensive and complex to maintain or adapt to changing environments by the early 1990s, further eroding the commercial foundation of symbolic AI. Remarkably, the AAII, Association for the Advancement of Artificial Intelligence, warned of the incoming AI winter as early as 1984, years before the Lisp machine market collapsed, demonstrating that industry experts sensed the economic bubble was unsustainable. Historical connection, the vicious cycle of brittleness. Expert systems found success precisely because they were narrow. Example, configuring one specific computer model or diagnosing a limited set of diseases. This narrow focus, however, highlighted the inability of symbolic AI to scale up to the general intelligence promised at Dartmouth. This failure to generalize, coupled with high maintenance costs, brittleness, caused the collapse. The simultaneous failure of major international projects, Lighthill in the UK and FGCS in Japan, demonstrates that AI disillusionment was a synchronized global retreat driven by a unified over-reliance on the symbolic logic paradigm. Act 4. Quiet Revolution, Algorithms of Resurgence. During the 1990s, while the public believed AI was dormant, fundamental scientific progress shifted the field away from logic-based rules and toward statistical and data-driven methods, setting the stage for the modern boom. This era solved the critical mathematical flaws that had plagued previous decades. The statistical renaissance, 1990s. The explosion of data from the emerging internet age provided the fuel necessary for statistical models to overtake symbolic systems. Fact 61. The emergence of knowledge discovery in databases, KDD, workshops in the 1980s and 1990s officially marked the shift towards automated pattern recognition, a foundational concept of modern machine learning that occurred quietly during the AI winter. Fact 62. In 1994, Business Week's story on database marketing highlighted that companies were actively drowning in data they couldn't manage. This established a critical commercial necessity that traditional symbolic AI was structurally incapable of fulfilling, creating the perfect demand vacuum for statistical AI. Fact 63. This explosion of data, later dubbed Big Data around 2005, drove the requirement for AI systems capable of processing information at unprecedented scales, giving a massive, undeniable advantage to statistical and probabilistic models. Fact 64. The renewed success of AI in the early 2000s was due to the precise convergence of three elements: powerful computer hardware, the collection of immense data sets, and the application of solid mathematical methods. Fact 65. The International Association for Statistical Computing, established back in 1977, aimed to link traditional statistical methodology with computer technology and domain expertise. This mission statement perfectly describes the data science approach that eventually resurrected AI, demonstrating the long gestation period of the statistical paradigm. Fact 66. Modern AI systems integrate highly technical analysis, such as using sentiment analysis, a subfield of natural language processing, to derive quantifiable sentiment scores from unstructured customer reviews. These scores can then be integrated with structured data, like transaction amounts, using statistical methods, e.g. Pearson's correlation, to derive actionable business intelligence. Mathematical elegance. Support vector machines, SVM. The 1990s saw clever mathematical techniques solve persistent problems of nonlinear data classification. Fact 67. The core support vector machine, SVM algorithm, which maximizes the separation margin between classes, was initially invented in 1964 by Vladimir N. Vapnik and Alexei Chervonenkis. Fact 68. SVMs, in their original form, can only produce simple linear boundaries between classes, a limitation that makes them ineffective for modeling the complexity of real-world data. Fact 69. The pivotal breakthrough that transformed SVMs occurred in 1992, published 1995, when Bernhard Boser, Isabelle Guyot, and Vladimir Vapnik suggested using the kernel trick to create powerful, nonlinear classifiers. Fact 70. The kernel trick is an elegant mathematical technique that allows linear classifiers to function effectively in an implicitly higher dimensional feature space, where the data points become linearly separable. Fact 71. The mind-blowing aspect of the kernel trick is that it bypasses the need to explicitly perform and store these computationally expensive high-dimensional data transformations. It relies instead on a kernel function that directly describes how points relate to each other, maintaining efficiency even in infinite dimensional spaces. Fact 72. The common soft margin incarnation proposed by Corinna Cortez and Vapnik in 1993 allows for a minimal number of misclassifications to occur. This critical practical allowance prevents the system from overfitting to noisy data, making SVM a robust, real-world tool. Fact 72. The common soft margin incarnation proposed by Corinna Cortez and Vapnik in 1993 allows for a minimal number of misclassifications to occur. This critical practical allowance prevents the system from overfitting to noisy data, making SVM a robust, real-world tool. Taking pause here, ending with sudden recognition. Your mind has the freedom to release tension. Your hope behind you be. Without the pain of fixing the problems, you will experience the peace of mind without worry. You are enough to know that you can do things. Solving the time problem. Long short-term memory. For sequential data, like speech or text, a fundamental mathematical flaw, known as the vanishing gradient problem, was solved, enabling highly sophisticated models that could finally remember context over long time sequences. Fact 73. Traditional recurrent neural networks, RNNs, used for sequence modeling, struggled severely to learn dependencies when the time interval between relevant input events was long. Fact 74. This critical failure was caused by the vanishing gradient problem, where the error signals used to adjust the network's weights rapidly decayed as they propagated backward through time, effectively giving the network no memory. Fact 75. In 1995, Jürgen Schmidhuber and Sepp Hochreiter introduced a novel, efficient, gradient-based method called long short-term memory, LSTM, to address this specific issue. Fact 76. LSTM solves the vanishing gradient by enforcing constant error flow through constant error carousels within special units, allowing it to successfully bridge minimal time lags in excess of 1,000 discrete time steps. Fact 77. The LSTM unit is composed of a cell which remembers values and 3 specialized multiplicative gate units, an input gate, an output gate, and the crucial forget gate. Fact 78. The forget gate is the ingenious mechanism that learns what information to deliberately discard from the previous state, assigning a value between 0 and 1, which selectively regulates the flow of information for long-term dependencies. Fact 79. LSTM's ability to process sequential data and keep its hidden state over thousands of time steps made it insensitive to gap length. This capability led to wide applications in fields like speech recognition and machine translation. Fact 80. The invention of LSTM, 1995, is considered a key breakthrough that overcame the vanishing gradient problem in RNNs, serving as the necessary architectural backbone for the development of sophisticated natural language processing (NLP) systems until the arrival of the transformer architecture. Historical connection: solving the fatal flaws. The revival of AI in the 1990s and early 2000s represents the mathematical repair of the 2 major historical flaws that caused the AI winters. The XOR problem, which Minsky and Papert outlined, solved by multi-layer networks enabled by data and compute, and the vanishing gradient problem, solved by LSTM. The latency of genius is apparent here. These theoretical solutions matured slowly, only becoming viable when data scale and hardware capacity caught up, proving that the technical progress was often decades ahead of engineering feasibility. Act 5. The Age of Giants: Deep Learning and Scale, leading to superhuman performance in specific domains, and ushering in the age of exponential scale. The Deep Learning Catalyst, 2012. The final key to the modern revolution was the combination of massive datasets and highly parallel processing hardware. Fact 81. The ImageNet project, initiated 2009, created a massive dataset for training image classifiers, containing over 14 million images across 21,841 different categories. This provided the necessary scale of data that was previously missing. Fact 82. The immense task of collecting and annotating the millions of ImageNet images relied heavily on human labor sourced through Amazon's Mechanical Turk platform. This reveals the hidden human scaffolding required to bootstrap the deep learning revolution. Fact 83. In 2014, researcher Andrei Karpathy estimated that even an expert human with concentrated effort could only reach a 5.1% error rate on ImageNet classification tasks. The theoretical human ceiling was later estimated at 2.4%. The true breakthrough occurred in 2012 when AlexNet, a deep convolutional neural network, won the ImageNet Large-Scale Visual Recognition Challenge by an astonishing 9.8 percentage point margin. AlexNet, the champion of 2012, had 60 million parameters. This demonstration of deep learning success convinced the entire technology industry that this paradigm worked, shifting attention from academia to commercial development. This breakthrough was only possible because specialized GPU power, specifically enabled by NVIDIA's CUDA API, had reached a point where training AlexNet's 60 million parameters became practical through highly parallel processing. Hardware finally matched the architectural ambition. Fact 87. The pace of advancement was staggering. By 2015, AlexNet was outperformed by Microsoft's Very Deep CNN, which contained over 100 layers and achieved an error rate of 3.57%, rapidly approaching and then surpassing the estimated human ceiling. L. The Algorithm of Intuition, AlphaGo 2016 to 2017. The victory of DeepMind's AlphaGo in the complex game of Go demonstrated that AI could achieve a level of creative intuition previously thought to be uniquely human. Fact 88. Deep Blue's victory over Garry Kasparov in chess in 1997 was largely a victory of computational brute force, massive search depth. By stark contrast, AlphaGo's victory in the complex game of Go was a victory of deep learning combined with Monte Carlo tree search, MCTS, achieving strategic intuition. Fact 89. The 1997 rematch saw Deep Blue defeat reigning world chess champion Garry Kasparov 3.5 to 2.5, marking the first time a world champion was defeated by a computer under tournament conditions. Fact 90. In the 2016 match against Go world champion Lee Sedol, AlphaGo executed Move 37 in Game 2, a move that professional commentators estimated had a minuscule 1 in 10,000 chance of being played by a human expert. Fact 91. Move 37 was not only pivotal in helping AlphaGo win the game, but also upended centuries of traditional Go wisdom, demonstrating the AI's ability to generate truly novel, superhuman strategy and knowledge. Fact 92. In response, Lee Sedol later played his own counter masterpiece, known as God's Touch, Move 78, in Game 4, which was just as unlikely and inventive as Move 37. Fact 93. Deep Blue's programmer, Sue, asserted that the 1997 contest was not man versus machine, but one outstanding man and the men who programmed the machine. This philosophical distinction began to blur with AlphaGo's intuition-based wins, which generated strategic novelty outside of its human programmer's knowledge. Fact 94. In October 2017, DeepMind introduced AlphaGo Zero, a version created without using data from human games, training purely via reinforcement learning, self-play, based only on the rules of Go. Fact 95. Starting tabula rasa, blank slate, AlphaGo Zero surpassed the strength of its champion-defeating predecessor, AlphaGo Lee, in just 3 days, winning 100 games to 0. Fact 96. DeepMind CEO Demis Hassabis explained that AlphaGo Zero was powerful precisely because it was no longer constrained by the limits of human knowledge, proving that reliance on human expertise had actually imposed a ceiling on the AI's performance capability. The Attention Revolution, an Exponential Scale. 2017, present. The final architectural shift allowed for the explosion in scale that characterizes the current generative AI boom, demanding unprecedented financial investment. Fact 97. The seminal 2017 paper, Attention is All You Need, introduced the transformer architecture. This architecture replaced the sequential, speed-limited nature of LSTMs and RNNs with a revolutionary self-attention mechanism. Fact 98. The self-attention mechanism enables the model to process all tokens in a sequence simultaneously and in parallel. This massive parallel computation, facilitated by high-end GPUs, made the training of trillion-parameter large language models, LLMs, financially feasible. Fact 99. The architecture of the transformer, lacking the inherent sequencing of an RNN, must explicitly add positional information to its input embeddings. This positional encoding is critical for the attention mechanism to correctly consider the relative location of tokens in a sequence. Fact 100. GPT-3 2020 demonstrated the extreme scaling limits of the transformer model, featuring 175 billion parameters, an order of magnitude larger than its previous record-holding rival, 41. The sheer economic scale of training GPT-3 was estimated to cost over strong $4.6 million, highlighting the transformation of AI research from an academic pursuit to a hyper-capitalized industrial endeavor. Fact, historical connection. The convergence of the triad. Modern AI boom is fundamentally the resolution of the AI winter narrative, characterized by the perfect historical convergence of the three necessary ingredients: data, ImageNet, hardware, NVIDIA CUDA GPUs, and architecture, AlexNet Transformer. The failures of earlier AIs were multivariate, but once all three components crossed critical maturity thresholds simultaneously, the field escaped its cycle of disillusionment. AlphaGo's Move 37 and AlphaGo Zero demonstrated that AI can operate outside the bounds of human knowledge, accelerating the strategic knowledge frontier beyond human input. Conclusions. The enduring paradox of scale. The history of AI is dominated by a persistent, complex paradox. The pursuit of artificial general intelligence (AGI) has repeatedly failed, yet the relentless focus on narrow, specialized problems has yielded spectacular, world-altering successes. The early symbolic systems, fueled by mathematical hubris, died because they were too brittle and expensive to maintain. The new statistical systems, fueled by unimaginable quantities of data and computational power, succeed because they are robustly probabilistic. The transition from the Lisp machines of the 1980s to the massive GPU clusters required for GPT-3 illustrates the shift from knowledge-based logic to computation-based probability. The training cost of GPT-3, over $4.6 million, signifies that the frontier of AI research is no longer accessible to small academic groups. This exponential scaling implies a new paradigm where the democratization of AI application via APIs and open models coexists with the consolidation of AI power, as only a handful of multi-billion-dollar corporations can afford to train the foundational models. The final conclusion drawn from the 100 mind-blowing facts is that AI progress is characterized by the harvesting of latent theoretical genius. Concepts like SVM and LSTM were shelved until the necessary hardware and data converged. This suggests that while today's systems feel revolutionary, their theoretical components may have been sitting patiently on academic shelves for decades, waiting for the massive scale of capital and compute to finally unlock their potential. The challenge of the current era is to manage the philosophical and ethical implications of systems that can now generate creative solutions outside the boundaries of established human knowledge, as demonstrated by AlphaGo's superhuman strategy. Thank you for watching. Please don't forget to like, share, and subscribe. See you again.